So I'd like to thank the organizers for giving me the opportunity to speak here before you. And so Jean-Paul, he's a great bridge builder. He has built through several years bridges from France to Mexico, from France to Brazil, from Brazil to Mexico. And nowadays, it's important that there are people which are in this integrating fashion. So in that sense, I think Jean-Paul's illustrates France's heart on the unity of humankind by sharing knowledge. So he has done great communication things with us in Mexico. So as always, I'm like a Buddhist, turning around a wheel which goes around a geometric problem, making it algebraic, then do some algebraic computations with geometric meaning, and then going back and forth to try to understand some geometry and to develop some algebraic techniques. So the problem which has demanded my attention during several years, and I don't think I have arrived at the end of this quest, but let me communicate to you the process that I'm with. So I would like to understand the relation of the vanishing cycles with the speed of zeros of vector fields tangent to the Milnor Fibre. So I want to use vector fields as a tool to understand singularities. And so what this means is the following. I'll always be considering a function with an isolated singularity at 0. And so we have the usual picture of these Milnor fibers. And now I want to consider a family of vector fields, xt of z. So these are vector fields which satisfy the relation, the derivative of f minus t applied to x sub t should be equal to f minus t times some function at of z. So the geometric meaning of this equation means that xt restricted to the variety vt, so vt is a set of points which satisfy the equation fz equals t, is tangent to vt. And then I consider gamma as the set of points in the TC plane, in the TC space, C cross Cn plus 1, in such a way that the set of points where the vector fields vanish. And I suppose that this is a curve, and this is the decomposition of the curve into irreducible components. And so, excuse me?
T is fixed or?
No, T is moving. T is a moving parameter. So in that sense, for T different from 0, we have a vector field which is tangent to a smooth fiber. And so it vanishes at a certain number of points. And then when I move the parameter T, these points are moving and they are approaching 0. And I would like to understand the rate of convergence of these vector fields in these components towards the origin, and to compare this with the vanishing cohomology of the Milnor fiber. So I want to relate the rate of speed of the zeros of the vector field with the topology of the Milnor fiber.
But the vector does depend on T, right?
Yeah, this depends on T. Who? The vector field. Yeah, the vector field depends on T, and so a typical example of this situation that I'm thinking about then is.
Is it unique for given T?
Excuse me?
Is it unique for given T?
No, what? No. So the thing, I want to understand the function, and then there are many vector fields which satisfy this condition. Many vector fields.
So the zeros are not defined.
Yeah, I fix f and fix xt. You fix the function and the vector field. Now, what I really want to understand is the function. So the vector field is a tool to understand the function. So I consider not only one vector field, but I want to consider all kinds of vector fields and try to see what would they have in common, these different components. So, or if you want to, in some sense, if according to the function f, perhaps we are forced to have gamma different kinds of irreducible components. So anyway, so this is the question which has motivating my research. I'm sorry, what's this? Yeah, so this is a typical example would be the following. You take an odd-dimensional space, and here you take the following a family of vector fields. You put f minus t of z in the first component, and then in the other even number of components, you do this Hamiltonian trick. So that when you write this df minus t applied to xt, then you get partial of f with respect to c0 times f minus t, and then the other components all vanish out. So in this case, the set of the zeros of the vector field, so here the zero set was in C cross Cn plus 1. Here's where I define this gamma tilde over here. And then I project to the Cn plus 1 to get this gamma, these curves over here. And so this is like the physical curves in Cn plus 1 space where the zeros of the vector field are moving.
About the first slide, where is where is differentiation in the last term?
I'm sorry. So this partial of f with respect to, I'm sorry. So yeah, I guess that. So I'm sorry. So this is partial of f with respect to C2. I'm sorry, I made a mistake there. Minus partial of f with respect to C1, partial with respect to C2, and so on. So like a Hamiltonian vector field, so that when I apply df, these two terms will cancel out. And so in this sense, this family of vector fields, if you look at its zero locus, the zero locus is exactly this polar curve in the sense of Bernard. And so one has these different components of the polar curve, and so that's what I want to understand, these invariants which are coming in from the zero locus and related to invariance of the singularity. So in order to explain this, then I have to explain what I mean by rate of vanishing cycles. And in that sense, I'm very pleased to have in the audience here Professor Varshenko, which many years ago introduced a procedure to analyze this vanishing, and which gives rise to this mixed Hodge structure that in some sense in Professor Dimka's lecture, he skipped this part because it's supposed to be more technical. So in that sense, I will have to deal a little bit with this mixed Hodge structure in vanishing cohomology, and that's where I'm going to look at the invariance. So also another motivation for what I'm going to explain, I'm not only interested in the complex case, but also same problem in the real case. So we have this real Milnor Fibre, we have a real analytic function with an algebraically isolated singularity, and we have real vector fields. The difference in the real case is that we now have a sign attached to each point, and we want to understand in the sense like Poincaré-Hopf theorem, this Poincaré-Hopf index theorem. So in the real case, so we have this, this would be the Milnor algebra, as was, so here I'm in the local situation. In Professor Dimka's lecture, he was speaking in the global situation. I'm restricting to the local situation, and in particular, I will be interested in understanding some behavior which appears for non-quasi-homogeneous singularities. So I'll be analyzing local situation of singularities in the non-quasi-homogeneous case. So in the complex and in the real case. So in the case of the real numbers, an invariant which appears is the following, is that so we take the ring of real analytic functions at 0 divided by the Jacobian ideal, and now also was not mentioned in Professor Dimka's lecture, but and usually is ignored, but this vector space, this algebra, this finite dimensional algebra, also has a non-degenerate bilinear form. And one of my points is trying to understand how to use this non-degenerate bilinear form. How do you use this? And so the way one defines it is very simple and canonical. You take the A has a product structure, the multiplication, and then you continue with which is bilinear, symmetric, and then you continue with a linear map. You choose a linear map that takes the class of the Jacobian determinant of f to a positive number. And so this algebra A is a wonderful algebra in the sense that it has a minimal ideal, and the minimal ideal is generated by the class of the Hessian, is one-dimensional, and the only thing important is that this linear map sends this Hessian determinant to a positive number. In the case of the original Grothendieck formula, this L applied to G is 1 over 2 pi I to the n plus 1, the integral of G dc0 exterior dcn, and here we put the partial derivatives, and we integrate along a cycle gamma, where gamma is the set of points where these partial derivatives equal to some fixed value epsilon, small value epsilon. So this is an n plus 1 real dimensional cycle that is being integrated on an n plus 1 differential form. This thing has poles where the partial derivatives vanish. This cycle does not intersect the pole, and so this is a closed differential form. So this number is defined in homology, and if G belongs to the Jacobian ideal, then we can cancel one of the factors. So if it's a multiple, if J is equal to F0 times some function H, we can factor the F0 and then apply Stokes' theorem, and this becomes 0. So in that sense, this linear function actually is giving is an example of this kind of L. And then in this formula, what we're doing in this bilinear product is G and H, is that here we are putting G and H. So we are using the product structure in the algebra here, but we want to understand the integral. Now, in particular, if one of the things I'm going to be interested in is in understanding what happens if I multiply by F here. So if I multiply by F here, now it is not true that you can take the F outside the integral. But in some sense, there are some relations between these ones and when you take different powers of R in this expression. And so this is what I'm going to be trying to understand, is this. So anyway, now a geometric interpretation of this algebraic bilinear form was given by Arnold, where he proved the following theorem, that if you have a real analytic function with an algebraically isolated singularity, the geometric meaning of this signature is that it computes either with a plus sign or a minus sign the Euler characteristic of the Milnor or real Milnor fiber on the right and on the left. So that's the geometric meaning of this signature here. Now, one can define finer versions of this bilinear form. So since we want to talk about rate of convergence of things, it means that we have to cut up things and say, so we're going to go like to the butchery and cut the Milnor algebra and cut the vanishing cohomology. We have to break it up into pieces, and each piece will have a different meaning. So in that sense, we have this algebra A. Now, and then what will be fundamental in the analysis I'm going to make, so this will have a non-degenerate bilinear form, and then this is the linear map induced on A by multiplication by F. In the case that F is quasi-homogeneous, it is equivalent that this map be the zero map. So if this map is the zero map, what I'm saying is not interesting. So I'm centering in the case when F is not the zero map. Then in this case, I will explain more, but the bilinear form will break up into primitive pieces, and then from the primitive pieces, we will make all the bilinear form. So this bilinear form, at first instance, it's concentrated on this Milnor algebra, but I want to show so that I'm going to be explaining these kind of pictures, which this is the Jordan block decomposition given by F, given by multiplication by F. So what it means is I'm going to, so F is a nilpotent map, so I can do Jordan block decomposition, and so this would be like a block of size 2, this would be a block of size 1, this is a block of size 3, a block of size 4, different kind of sizes of blocks, and so the annihilator of F, is the end part of, so if you view this as a pyramid, so applying F is moving a step like this. The annihilator is the set of places where if you move, you fall down the pyramid. So it's on one extreme. And now on this extreme, you can take, so in the kernel of F, you can, so this would be all this. If you take kernel of F intersected with the ideal generated by F, then, so this would mean which is the end points of the pyramid, but which have a previous step. So the ones above here, they don't have a previous step. So that's only this part over here. And so we have a flag. So this is the kernel of f divided by f squared. So this is like the eigenvectors. So these would be the eigenvectors which don't correspond to Jordan blocks of size 0. Then these ones would be the Jordan blocks of size 1, of size 2, of size 3. So we're distinguishing these eigenvectors by remembering where they came from. And so in this case, we can define a bilinear form, so kernel of f divided by f to the m times kernel of f divided by, intersected with f to the m So if you take an element G and an H here, then we want to define a bilinear form. So this is going to correspond to these primitive bilinear forms. Please. So here we have, if you take two elements over here, we want to define on F of order M, and the way to define this is going to be the following. Since G belongs to the ideal generated by F to the M, we can write G as F to the M times some function G prime. And so what we're going to do is we're going to do this product with respect. So we're going to divide by a power of F. And we are allowed, when we restrict to this piece, so when we are restricting to these pieces, you get these finer forms.
Do you divide H also by power?
No, only one. You can divide one or the other. And now this over here will be, when you divide by kernel of F intersected with F to the M plus 1, then here is the kernel of this form. And so in here we will get a non-degenerate bilinear form. So we are cutting up the bilinear form into primitive pieces, and I will show you how you can, from these primitive pieces, understand all the bilinear form. So I want to the Milnor algebra, I want to, with its bilinear form, I want to cut it up into pieces, and each piece will have an irreducible bilinear inner product, and one can understand the whole structure of the bilinear form by understanding these pieces. There's a procedure to make this.
Why is it non-degenerate?
You have to prove, but it's non-degenerate. So one has to prove this, but it's non-degenerate. So and then this formula appeared because then what this means is that we have then this, in the real case, we have this signature, which is the signature of A, and then we have this signature of A1, signature of A2. We have these smaller pieces, and so on. And so I had a previous formula, a previous theorem proved with Giraldo and Mathématiques that says the following thing. So if you take a function with an algebraically isolated singularity, a vector field with an isolated singularity satisfying this relation. So this is the relation we get in the limit when t goes to 0 in the previous example. And so how to compute the index of this vector field on the singular situation. So we had a formula that looked like this. And here these constants k plus and k minus are the sum of these pieces, of these primitive pieces, and in the negative case, for the negative Milnor Fibre, it's alternating signs. So in some sense, I want to understand where do these constants come from and why do they have to appear in the formula. So this is the first time I was faced with understanding these numbers over here, is because there was a constant which here is independent of the vector field. It just depends on the function, on the variety defined by the function. And so, so there was this constant, normalizing constant. So we had to compute this constant, and it turned out that the constant was these values over here. And so I was there to...
What is the definition of in v plus minus 0? What is the definition?
What's the definition of this?
Yes.
Right. So the thing is... So here we have x sub 0 is a vector field which is tangent to v sub 0. And so we take v plus, say, and so we transport the vector field, we restrict x0 to the boundary of v0, and then transport it to some vector field y0 on the boundary of vt. So we just move the vector field from here into these ones. These two are isotopic boundaries. Then we extend the vector field in any way. We look at the set of zeros. We put the extension in general position, and then the index of x0 at 0 on v0, on v plus, will be equal to the sum of the indices of this vector field yt on vt at those points where it vanishes. So we are transporting, so the vector field is vanishing here at the origin, and we want to figure out what the index is of this vector field. And so the way to do is you transport the vector field on the boundary, put it in general position, extend it in general position, you have a finite number of singular points, and then you add them up. And then you do this also for the negative. Now, since the Euler characteristic of the positive part and the negative part does not necessarily coincide, then this index depends on whether you extend it on the right or on the left. And so these constants here, which make the difference whether you compute the index on the right or on the left, are these constants, which are independent of the vector field, and they are given by this, the signature of this bilinear form in these pieces. So I wanted to understand why are these? So this is a product of a computation. By computation means we obtain this formula. But now we want to understand why are these terms here and what do they mean.
And sigma b0 is what?
Excuse me?
Sigma b0. What is sigma b0 in the right hand side?
So this is something which I'm not explaining. So this means this is some algebraic procedure similar to this. So this b is O divided by x0 xn. So this would be the multiplicity of the vector field in the ambient space. Here we have the class of the determinant of the derivative of x. So we take its class here. And then again, this guy generates the minimal ideal. And then we want to take b divided by the annihilator. So we have df applied to x is equal to h times f. This is the tangency condition for the vector field on the fiber f equal to 0. And so here we take b divided by the annihilator of h. And here we have an element which is the Jacobian of x divided by h. And so you repeat the same procedure. You can construct the bilinear form on this space using this as the socle of this algebra. And so this gives a non-degenerate bilinear form, and then the signature of this one is this one over here. So there is a procedure, an algebraic procedure, to compute these numbers depending on x. But the surprising fact of this is that in this formula, there are these constants which are independent of the vector field. So this just depends on the variety. So what's the meaning of this, and why are they there? And why on the right is one, and then on the left is the other? Why the formulas are like this? So in that sense, this is like, for me, the challenge to understand all this. So as I mentioned, so this is like a walk in a forest. I have, many problems, and I want to figure out some answers. So so let me begin again. So this was like an introduction. Any questions? So now, so we're going to take a holomorphic function with an isolated singularity. There's this fundamental number, the Milnor number, which topologically is the dimension of the set of vanishing cycles, and algebraically it is measured in this algebra sense. From now on, I'm going to be sticking to the complex case. So, so first, I want to state the theorem we have obtained, and then explain the geometry, and then explain some words about this. So, as I mentioned, so we have this bilinear form, this Grothendieck bilinear form. So we have this form over there, which I call this AC, which goes from this Milnor algebra times the Milnor algebra to the complex numbers. And I want to consider the form, as analysts do, that you consider a bilinear, an interior product, and then you take here a symmetric operator, and you construct a new inner product, putting this F over here. Now, this now becomes a symmetric bilinear form, but now it is degenerate. So this degenerates in the annihilator of F. So this now becomes a so this becomes a form which it degenerates in some space. Now I want to so this is the algebraic point of view. The topological point of view is going to be the following. We're going to take the vanishing cohomology. So here we're going to denote it like this. So this is vanishing cohomology. So let's put a fixed some point, a cohomology. So this is vanishing cohomology. And here we have a non-degenerate bilinear form, which is going to be induced by coproduct. So I will explain in a slide which comes later how I do this, but this is going to have a non-degenerate bilinear form. And then n is going to be the logarithm of the unipotent part of the monodromy. So the monodromy map will decompose as a product of its semi-simple part, which contains the information about the eigenvalues, and the unipotent part, which contains the information about the Jordan blocks. So n is the logarithm of this unipotent part, and it's also a nilpotent matrix. And so we can play on this space, and n is antisymmetric So we want to play around with n, with this, well, this form Q. We want to put an n over here. So n is also a nilpotent matrix. Now, this bilinear form is I will explain, is neither symmetric nor antisymmetric. It's symmetric in one piece and antisymmetric in another piece. This one over here. And so every time I put an n into this bilinear form, if it was symmetric, it will become antisymmetric. And if it was antisymmetric, it will become symmetric. So in this other situation, we were always speaking about symmetric forms. In the topological case, so this so the theorem we have obtained is going to say the following thing. So we want to compare this degenerate bilinear form with this degenerate bilinear form, and our claim is that so this one consists of two additive terms. The dominant, to explain dominant in which sense, I have to introduce this mixed Hodge structure to explain. So this bilinear form will have a dominant part which corresponds to this bilinear form applied in the vanishing cohomology, and it has a remaining form. The other summand of this description is a geometric, non-topological, and I will explain this, binding of two n-Jordan chains in cohomology to one Jordan chain in the Milnor algebra. So I want to relate the Jordan chains in the Milnor algebra with the so F Jordan chains with respect to multiplication by F, and then Jordan chains of n, and then I want to show that this bilinear form is in some sense measuring information on the binding of these bilinear forms. Okay, so first I want to illustrate in an example, because as it's going to become a little technical, let me at least give you the idea of what I want to say. So the thing is the following. So here we have this algebra A, and we have these different Jordan blocks, which are obtained by multiplication by F in the algebra. The thing that we have a non-degenerate bilinear form implies that the Jordan chains are going to come in pairs, one, and it's dual. So that's why, see, I'm writing it, so these are like, they come in pairs. Now, perhaps there are some which come alone because they are self-dual. So in that sense, we have two kinds of Jordan cells, which are the ones which its dual is another Jordan cell different, and then we have the ones whose dual is the same one. Now, in here, so I'll have to explain how to construct a map which goes from the Milnor algebra to vanishing cohomology. And then, so here I put the Jordan chains which are given by multiplication by F, and here I put the Jordan chains which are produced by N in vanishing cohomology. And I want to figure out what's the relation between the two. And so the relation will be that there are a finite number of these chains which are broken up. So in here, we're breaking up this one in this piece, so we will remove this. So this means that when we take its cohomology, this one over here, instead of going to this one, will go to 0. And so in that case, we broke it up and it becomes a chain like this. And then this one over here, since now there is not a thing which connects this one over here, then it appears on this other place. Now, this primitive cohomology which I was explaining here, so this annihilator are the end of the chains. but the end of the chains is the same as the beginning of the chains, where you are just pushing with the F. So let's say the result we have is that we can understand the relation between these bilinear forms in the algebra A and this bilinear form in this cohomological algebra, which is produced from breaking up this, and this will give the principal term. Now, where does this other geometric form comes about? So this is what I call this the binding of these topological chains. So this is the binding, and so this will give rise to this. This binding is the one which produces this other bilinear form. So anyway, so that's more or less this picture. Now, I want to go to a very concrete example. Okay? So the very concrete example is this equation, x5 plus x4y plus y6. So in this example, what the situation is the following. So the Milnor number, so these computations were done with singular, and so the Milnor number is 19. Now, the degree of the equation, when you view it globally, is degree 6. A degree 6 equation in P2, so if we take a smoothing of this, so f equal to t, and view it in projective space, the genus will be 10. So this means that the dimension of H1 is 20. And so we can view and also this equation is reducible at 0. And it looks like this. So it looks, so here we have, so here we will have this 9-dimensional genus 9. So we have this genus 9 over here, and in here, when we're coming out over here, it will have two components. These two components are representing the fact that this has two irreducible components, and then we have a point at infinity, which is tangent at infinity of order, and so we have like a pair of pants. Here's the point at infinity, which is a branch point, a tangent point to the line at infinity of order 6. And now, if we consider the monodromy map of this, so here I am writing the eigenvalues for mu equal 19. So they are all 24th roots of unity. 0, all of them have multiplicity 1. So here eigenvalues all have multiplicity 1. Now, if you consider it the homology, not vanishing homology, but actually the homology of all this smooth fiber, then it's dimension 20, and in 0 we have a Jordan block of size 2. Jordan block of size 2. Now, so here, if we look at the eigenvalues, we get these numbers. 4, 8, 12, 16, and 20 don't appear. So these are the other 19 numbers. So here are the 19 numbers. But now you notice that I pictured them with colors. A person which only sees eigenvalues would look at this and he doesn't see the colors. So the colors are going to come in because of the mixed Hodge structure that this has. In this case, for this example, in the local situation, n will be 0. So there is no weight filtration. Here, weight filtration is trivial. So we only have the Hodge filtration. And so the Hodge filtration means that these are these blue points, and then this is the green points. And in here, we can see the symmetry between in this Hodge structure, because since the n is 0, it has a Hodge structure, not a mixed Hodge structure. And so in this sense, we can see this, the symmetry between these two, right? And so here we are looking at the spectrum. So the spectrum is the choice of a logarithm of an eigenvalue of the monodromy. But we don't do the choosing. The choosing is done by the function, and that's this mixed Hodge structure appearing here. Now, in here, if we now choose eigenvectors for each one of these eigenvalues. So Sj, we have this 19, and now the bilinear here, this bilinear form. So 0 is special. 0 is a special point in the sense that for 0 we do have to consider Sn. So if here S is the alternating, so here since this is one-dimensional, the bilinear form is alternating. So when we put the n, we transform it into a symmetric bilinear form. So even though the bilinear form here, coproduct, is alternating, when we do this, we put the n restricted to this eigenvalue, to the eigenvalues 0, or to the eigenvalue 1, then this becomes a symmetric form. So we will have a symmetric form defined at this point, and for the other ones is antisymmetric, and then we get an orthogonal direct sum where we put this one with this one, this one with this one, this one with this one. So this is the expression of the bilinear form in coproduct. Now, we are going to choose. So this thing of choosing is from this Morito-Saito way of choosing these H's, and as also developed by Hertling. And so one chooses holomorphic functions in such a way that if you consider the two form, the function times this differential form, the principal part, so this term is something which I have to explain. So given the two form, we will be able to expand it as a section of the cohomology bundle, and it will have a principal term. And so we choose these functions, holomorphic functions, in such a way that their principal topological term are the previous basis that we choose for this cohomology. And now what happens is the following. Now we're going to multiply by f these functions and see the expression of these functions in terms of the other functions that we define, and it turns out the following. So multiplication by f will correspond to multiplication by t when we consider the sections of the bundle, of the cohomology bundle. So this one, which is the smaller one, will be sent to this one, but here there is no point. So this is representing the thing that n is 0, n is 0. But multiplication by f is not going to be 0. It's going to have some terms which correspond to these functions on the eigenvalues which are to the right of here. So in that sense, multiplication by f, even though when we take topological part, it will have a 0, then in the algebraic part, it is not 0, it has these terms. It has this term. Now, if we do this with H2 and then we multiply, then it goes over here, so it's again 0, but then it has this contribution from the last holomorphic function. So from the point of view of topology, we apply and we get nothing. But in the algebraic setting, we get something, and so we start getting these numbers, A, B, C, and one can prove that these numbers, they put up, so when you organize this, it becomes the bilinear form, which is multiplication by f, and then doing this Grothendieck product, is going to be have this form. And so this is the bilinear form I'm talking about. So there will be, so this means that the bilinear form f multiplication by f, then in an adequate basis, then it will have first a topological part, and there will be another part coming in after, which is the cause of this is because the multiplication by f, it does not only take into account what is the principal term, but also it has some other terms. And so with these other terms is where we get this. So in this example, what would happen is the following. So this would be the Jordan chains for A. All of them are one-dimensional, except 2. So multiplication by f, the image has rank 2. So multiplication by this, by the f we're considering, has rank 2. If we consider the n is 0, so the Jordan blocks here are these ones over here. So in this case, we are deleting these 2 arrows when we pass from algebra to topology. And the new bilinear form would be the following. So you take the annihilator of f, so it would be these 2. We have a bilinear form in these 2 spaces. And so how do you do? You take this one and the other one. One of them you take it one step back, only one, as I mentioned here, and then you do the coproduct of this one with this one. And so this gives the bilinear form. So the bilinear form is produced by taking the coproduct of these two any elements in the annihilator of f, but one of them you take a step backward and then you do the coproduct. You're dividing by f. And so this is a non-topological thing because in the topological sense you only have n, which is 0. And so this you do not see in the topology. It's coming in from the algebra, and my interpretation of this is this picture. So this is the picture which you have to remember of what I say. What did I say? You see, you have these Jordan blocks. Now, the basis of this is a paper which I have been studying for some time, which exactly was written by Professor Barchenko many years ago, which is multiplication by f in the local ring and its relation with topology, where he explains how when you take the grading, and this I thank Professor Nemeti here, which once I was giving a similar lecture many years ago, and I had overlooked that in Professor Barchenko's paper, you had to take the grading with respect to the Hodge filtration in order to have this diagram agree. So, okay, very good. So in that sense, I'll pass you quickly to show you what I was going to explain more. So this is going into this mixed Hodge structure, which anyway I was not going to be able to explain in short time. So this means that there's a lot of this kind of thing, but I think I passed you the main idea. So thank you very much.